Next, we're going to talk about studying chemical reactions. If we're going to consider a chemical reaction, let's say we have reactants in equilibrium with some products. Okay, sometimes I'll refer to these reactants as starting materials. Might abbreviate that SM, a little short for reactants. If we take a look at a chemical reaction such as this, what are some of the things that we can investigate about that? What are some questions we can ask and things we can study? One area of interest is the area of chemistry called thermodynamics, and that's where we compare the energy or the stability of our reactants or starting materials and compare those to the energy of our products. Okay, and using thermodynamics is going to help us be able to predict the direction of this equilibrium. Is the forward reaction going to be favored, in which case we would build up our concentration of products, or is the reverse reaction we favored, in which case we build up the concentration of our reactants? Now, to describe the direction of this equilibrium, we use an equilibrium constant, and that's called KEQ. And KEQ is always defined as the concentration of the products divided by the concentration of the reactants. So if you have KEQ equal to 1, that means you have exactly the same amount of reactants and products, and they're converting the forward reaction and the reverse reaction, of course, in any equilibrium are occurring at the same time, but you never have a buildup of one or the other. Okay, but if you have a KQ that's greater than 1, if we take a look at this ratio, a KQ greater than 1 means that our concentration of products are going to be greater than our concentration of reactants. So we would describe that as the forward reaction being favored. The forward reaction is favored because we have a buildup of products. If the KEQ is less than 1, is a very, very tiny number, that means our denominator here is the larger value. The concentration of reactants is greater. And so that means that the reverse reaction is favored. So if we're asking in which direction an equilibrium lies, we can either ask, is it forward or reverse? Or perhaps we can ask it in terms of KEQ. Is KEQ greater than 1 or less than 1? Another equation that's going to be important to us in thermodynamics is the following. Delta G equals delta H minus T delta S. And here delta H is our Gibbs free energy. This describes the spontaneity of a reaction. The delta H is our change in enthalpy, or the heat of reaction. And the delta S is our change in entropy. Now, for an organic reaction, most organic reactions, this value is usually very small. Now, it might still have an impact depending on the temperature of a reaction, but since delta S is usually a very small number, this value is typically insignificant or very often insignificant. So for organic reactions, we find that delta G is very often nearly equal to delta H. So a lot of times you're going to see reactions or descriptions where delta H and delta G are used somewhat interchangeably in the context of organic reactions. That's often the case. Now, if we take a look at an energy versus progress of reaction diagram, the way it's going to look is going to vary depending on whether we have an exothermic reaction or an endothermic reaction. So let's look at each of those one at a time. In an exothermic reaction, let's assume we have just a single step mechanism. Our starting materials are going to be at some initial energy, and our products are going to be at a lower energy. This difference in energy between the starting material energy and the product energy is defined as our delta H, our change in the enthalpy of the reaction. So in this case, because we started at a higher number and ended at a lower number, our delta H is less than 0. That's how we define an exothermic reaction. Now, the pathway to get from the starting material to product is not just simply a downhill run. We need to go through a high energy state called a transition state. TS stands for transition state. This is where we have a high energy complex We have partial bonds, bonds that are starting to break, bonds that are starting to form, partial charges, charges that are developing or dissipating. That's what a transition state looks like. And in order to go from starting material to product, you need to pass through this transition state in order to get down to product. Now, the energy required to get up to that transition state is defined as E sub A, and that is the energy of activation. Sometimes this is defined as delta G double dagger. You might see that sometimes. The double dagger is something that often refers to a transition state species. So what are some things that we can observe about an exothermic reaction? Okay, we said that the delta H is less than 0. It's a negative change. And that means that our delta G is also going to be less than 0 for a typical organic reaction where the delta S term is very small. Okay, and so that tells us that the products are favored. The products are favored because the products are the lower energy species. They are more stable. And so if the product is favored, what do you expect for the KEQ? How would you describe the KEQ? That's going to be greater than 1 because the products are in the numerator, so it's going to be a large number when we look at that KEQ ratio. Products are favored, KEQ is greater than 1, and we describe the forward reaction as being spontaneous. The reaction where we are going from starting materials to products, again, is our general reaction that we're looking at. In an exothermic reaction, we would typically translate that right to being a spontaneous reaction for organic chemistry because we're going in a direction of lower energy products. An endothermic reaction is one in which we start at a relatively low energy for our starting materials and our products end up in a higher energy. I seem to have exaggerated that a little bit more. Okay, but still, in order to get from the starting material to the products, we're going to have to go through some kind of transition state. And so this is what an energy diagram might look like for an endothermic reaction. Again, we can identify our delta H is always the difference between the starting energy and the final energy. That's the overall change in the heat of the reaction. And how would you describe this change? If we start out at a lower number and we end up at a higher number, that's a positive change. It's going to be delta H is greater than 0. Just like if you start out, if you have $10 in your wallet and you go to the bank and you take out money and you now have $100 in your wallet, that is a positive change. You've increased the amount of money you have. So that would be a delta H of greater than 0. And that must mean that our delta G is also going to be a positive number, greater than 0. Delta H greater than 0 tells us it's an endothermic reaction. Energy is consumed. Delta G greater than 0 tells us that this reaction is not a spontaneous one. Okay, because the reactants are lower energy, the reactants are the ones that are more stable, so the reactants are favored. How would you describe the KEQ if the reactants, the starting materials, are going to be more stable? The reverse reaction is going to be favored, is going to be the spontaneous one, so our KEQ in this case is going to be less than 1. And we would say that the reverse reaction is the spontaneous one, or we would describe the forward reaction as the non-spontaneous one. We can also point out here again our energy of activation is always the energy required from the starting material to achieve the transition state. So there's a few things that we can label on our energy versus progressive reaction diagram. Now we can estimate the delta H of a reaction on whether it's going to be an exothermic or an endothermic reaction by taking a look at the types of bonds that are being formed in the reaction and the bonds that are being broken. Now one of those processes, bond breaking and bond forming, one of those processes requires energy, one of those processes produces energy, releases energy. And it's very common for students to have a misconception on which is which, or not a firm grasp on which is which. So let's imagine having a stick and trying to break the stick. What do you have to do to break that stick? you have to put energy into the system, you have to put force into the system in order to snap the stick into two. Well, guess what? Chemical bonds are the exact same. Bond breaking is a process which requires energy. In other words, the delta H of such a reaction, if all we do is we broke a bond, that would be a positive delta H. It would be an endothermic reaction. Okay, that must mean that the opposite process, any reaction which forms a bond, is something that releases energy. And such a reaction would have a delta H that's less than 0. It would be an exothermic reaction. So this is a very important chemical fact that you should have solid, and that is that bond breaking is something that's difficult to do and requires energy, costs energy, and bond formation is a very favorable process. It releases energy. It's an exothermic process. Now, knowing that this is true, what we can do is we can use a table of average bond strengths to estimate the heat of the reaction. We can look at what's known as a bond dissociation energy to decide the relative strengths of the bonds that are being formed and the bonds that are breaking. So let's take a look at a sample of a table that might show some bond dissociation energies. And bond strength is defined or described by the standard bond dissociation energy. You could call that BDE for short, or DH naught. And that is defined as the energy required to break a bond in a homolytic fashion when in standard conditions and in standard states. So we're going to take this hydrogen-hydrogen bond, for example, and break it so that one electron goes to the left, one electron goes to the right. So our two products are two hydrogen atoms. We describe that as a homolytic cleavage because they each get one electron. They get the same thing. And the heat of this reaction is plus 104 kcals per mole. Does that make sense that it would be a positive number? Yes, because in order to break a hydrogen-hydrogen bond, you must have to put energy in. So this is an endothermic process. Well, you can find in any textbook a table of such energies. These are average energies, so you can read the table as such. A hydrogen-hydrogen bond is worth about 104 kcals per mole. A hydrogen-carbon-carbon bond is 99, and so on. Okay? And a few things that are maybe interesting to point out about this table is we can see a trend here. When we go down the periodic table, we go from fluorine to chlorine to bromine to iodine on hydrogen. You see that it becomes easier and easier to break that bond. Okay, and the trend we have here is that our bonds are getting longer. And longer bonds are going to be weaker. That's something that we can observe in this. Another interesting thing to see is something like, let's say a carbon-hydrogen bond or a carbon-carbon bond is worth about 100 kcals. Let's take a look at an oxygen-oxygen bond. That's a very low number. That's a very weak bond. As is, a nitrogen-oxygen bond, all these. When we have something like an oxygen-oxygen, or any two very electronegative atoms attached to one another, this is also a bond that's very weak and very easy to break, as we can see by these average bond dissociation energies. Or let's see, we also have, a chlorine-chlorine bond, for example, is or a bromine-bromine bond. Very weak bonds that are easy to break. I also see a number that kind of jumps out here. Silicon-oxygen is an extremely strong bond. Silicon loves to bond to oxygen. We'll see some examples of that way down the line. And then another thing that's interesting to note is to compare the strengths of single bonds, sigma bonds, to double bonds. So down here we have some examples of multiple bonds. For example, we could take a look at a carbon-carbon double bond. If we were to totally break this carbon-carbon double bond, it would cost us 146 kcals per mole, or we would get 146 kcals per mole if we were to form a carbon-carbon double bond. Now a carbon-carbon single bond is worth about 100 kcals per mole. So what does that tell you about the strength of a pi bond compared to that of a sigma bond? In order to break the sigma bond, you have to put in 100 kcals, but it only takes another extra 50 kcals or so to break that pi bond. So this is demonstrating to us that pi bonds are weaker than sigma bonds. It's easier to break a pi bond, and it's going to be more difficult to break a sigma bond. Okay, but let's take a look at an interesting example. How about a carbonyl? This is called a carbonyl. A carbonyl, when we have a CO double bond, is a very important arrangement of atoms called a functional group. It's a very important functional group because if we compare the energy of a CO single bond, a CO single bond is right here. It's worth 86 kcals. So if we were to have a double bond, what would we expect that energy to be? Well, 86 times 2 is 172 kcals. So if it was worth twice as much as a sigma bond, we would expect it to be 172. And we expect that a pi bond is weaker, so we would expect a carbonyl to be somewhere less than 170 kcals per mole. But look at the number. It's actually more. It's actually greater. All these CO double bonds have actually more energy in them than two separate CO sigma bonds would have. So that tells us something very special about the carbonyl, is that it's very stable, it's very strong. It's because it has resonance, stabilization. And so again, carbonyls are going to be a very important functional group to us. We'll see any reaction that forms a carbonyl, let's say, would be a very favorable reaction. We'll see lots of those. Okay, and you can see that there's slightly different numbers here depending on the structure in which the carbonyl exists. This is for carbon dioxide, and this is if we have an aldehyde. That means that the carbonyl has a hydrogen attached. This is for a ketone. That means there's two carbons attached to this. So, again, these are just average values, so you can see that there's some slight differences. So what we can do is we can use a table like this to estimate for a given reaction whether or not it's going to be exothermic or endothermic. So let's take a look at an example here. Here are our starting materials. They're combining and reorganizing to give this product. Now, to estimate the delta H of a reaction, it doesn't matter what the path is to go from your starting materials to the product, because remember, in thermodynamics, all we're doing is we're comparing the energies of our starting materials to our energy of our products. The path taken to get from here to there is not relevant. So what we can do is we can inspect this reaction and see what bonds have been broken and what bonds have been formed. So here we have a carbonyl in our starting material, and that carbonyl is gone. So we see that we're breaking this CO double bond. And we are also breaking this CH bond is no longer here in the product. These two CH bonds are still there. So the bonds that we're breaking are a carbonyl and a CH. And the bonds that we're forming are going to be this OH bond is new. There is no OH group in the starting material. This CO bond is new because the way that we do this calculation is we assume that we're completely breaking this CO double bond and then reforming the CO single bond. That's not really what's happening in the mechanism, but again, the math works out the same. And then this carbon-carbon bond is a new bond that's going to be formed in the reaction. So what we can do is we can look up these values on our table. The aldehyde carbonyl was worth 176 kcals. The CH was an average of 99. The OH was 111. The CO is 86. And the CC is an 83. Carbon-carbon bond is 83. And what we can do then is we can add up how much energy did we have to put into the system to break those bonds. So we add 176 plus 99. That's the energy consumed from the bonds broken. And then we subtract from that the energy released from the bonds that are formed. These are the bonds formed. And when we do this math, we see that we come up with an overall minus 5 kcals per mole as our overall estimated delta H. So does that tell us our reaction is exothermic or endothermic? If our delta H is less than 0, this is an exothermic reaction. So based on thermodynamics, is this a favorable reaction? Yes, this is a favorable reaction. We would expect it to be spontaneous, something that the forward reaction is going to be favored based on thermodynamics. Another thing that we can study for a chemical reaction is the kinetics of the reaction, and this is where we take a look at the rate of the reaction or the speed of the reaction. Maybe it's a favorable reaction, but it's very, very slow or it's very, very fast. What can we study when we look at kinetics? Well, let's consider a reaction such as this. Let's say we have A and B as our starting materials and C and D as our products. And this equation, this reaction, could be described by a rate expression as shown, where the rate is equal to some kind of rate constant that's defined at a given temperature. So rate studies are done at a given temperature to come up with this rate expression. And the rate will be dependent on the concentration of your starting materials, A, to some exponent, little a, and the concentration of B to some exponent B. And the way that this rate expression is determined is experimentally. This is experimentally determined. The concentrations are varied and the rate is measured, and that's how the exponents are set. So here's an example. In this reaction, we have chloromethane reacting with hydroxide to give methanol and chloride. When this reaction was studied, the following observations were made. If the concentration of the hydroxide starting material was doubled, then the rate doubled. In other words, the reaction was twice as fast to go to completion. And if the concentration of the other starting material was doubled, then the rate also doubled. So based on this experimental evidence, the rate for this reaction is described as K times the concentration of hydroxide times the concentration of the chloromethane. Each of these is just to the first power, because if you double this number, you double the rate. If you double this number, you double the rate. So they have a one-to-one correspondence. The way we describe this reaction, given this rate expression, is we say that the reaction is first order with respect to each of the reactant. That simply describes the exponent, which is 1 in each case. And we describe the reaction as being second order overall because we add up the exponents to describe the overall rate, the order of the overall rate. So we're adding a 1 and a 1, so it's a second order reaction. We're going to be using those terms later on, so it's good to review some of these kinetics principles. Now, what are some things we can do to speed up a reaction or slow down a reaction? We call these reaction rate variables. And remember, to do our reaction, we need to achieve our transition state in order to go from starting materials to product. Let's review that we have our energy versus product of reaction, progress of reaction diagram, and whether a reaction is endothermic or exothermic, either way, you still need to go through some kind of transition state to have that product, have that reaction occur. And so what we need is a collision. If we have more than one starting material, we need a collision of those molecules to occur with enough energy to reach up to this activated complex, this where we're starting to form bonds and break bonds, this transition state. So what are some things we can do? Well, one thing we can do is we can increase the temperature. If you increase the temperature, we increase the rate. Now, this is true whether you have an exothermic reaction or an endothermic reaction. This is always going to be true. We speed up a reaction by heating it up. Well, what's happening there is if you heat up a reaction, you increase the kinetic energy of the molecules. In other words, they're moving faster. Now, if you imagine a solution with our starting materials stirring around in the solution, and you heat it up, and now they're all stirring around, they're moving around faster, what happens is when they collide, that is now going to be a high energy impact, and what you'll end up with is more collisions have the necessary energy to achieve the transition state. Okay, so our reactions are going to go faster the hotter the condition is. This is why certain reactions like food spoiling, that's going to happen faster at room temperature or faster in hot foods than in cold foods. That's why we store our food in the refrigerator. That's why maybe you store your batteries in the refrigerator or your medicines in the refrigerator. The colder you keep them, the slower all the reactions that might happen for degradation. Okay, another possibility is we can increase the concentration and we can increase the rate. We just saw on the previous slide how that the rate expression shows the rate being proportional to the concentration of the starting material. So if we increase that concentration, you increase the rate. Now, how is that happening? What we're doing here is we're going to increase the probability of having of collisions. So if you have more molecules in a smaller area, it's more likely that they're going to collide, and therefore a reaction proceeds at a faster rate. And finally, if there's some way to one thing I can point out for these first two to describe it is if you think of our molecules that are colliding as if they're bumper cars. Let's say we have two bumper cars that need to collide at a certain speed in order for a reaction to occur. Okay, so increasing our temperature is like having our bumper cars racing around a lot faster. And if they're racing around, then when they do collide, it's going to be a very high energy collision. If they're going very, very slowly, if we have a nice, cold temperatures, it slows down all our molecules. And so when those bumper cars do collide, they're going to do so very low energy, and that's not going to cause a reaction. So most definitely a relationship between temperature and rate. Increasing the concentration, if we think about our bumper cars, it's like having, let's say we have 10 bumper cars, and we spread them out all over the United States, let's say, and they're wandering around the United States. Now, how likely is it that they're going to collide? Very unlikely, and therefore it's going to be a very, very slow reaction if that reaction requires a collision. However, if we take those 10 bumper cars and we put them in the room with us, in our classroom, and have them racing around, well, of course, they're more likely to collide, and therefore a reaction is going to happen faster. So increasing the concentration is another way to increase our rate. And the last way to increase our rate is if somehow we could decrease our energy of activation, that would make it a faster reaction. So where was our energy of activation? It was right here. It was the energy required for our starting materials to reach this transition state energy. So if we could decrease the height of the hill that we have to climb, we could do that by somehow stabilizing, bringing the energy of the transition state down. By stabilizing the transition state. If somehow we could stabilize the transition state, that would be a faster reaction. Okay, how can we do this? Well, there's a few different things that we might find. It can be done with solvent effects. Certain solvents might be better at stabilizing a transition state than others. You could have steric effects when you have crowding. That's going to be something that maybe raises a transition state energy, or reduced crowding will lower it. That will make one reaction faster or another. What's another way? Have you ever seen a reaction diagram that looks something like this? Have you ever seen that picture where suddenly a different path is taken that's lower in energy? What did that? Perhaps if we added a catalyst, that would be a way that we could lower our transition state energy. So that would be the role of a catalyst, and of course catalysts are there to speed up a reaction. Okay, so all sorts of things can be used to decrease our transition state energy, and the key is that if we have a lower transition state energy, we have a faster reaction. And we're going to see lots of examples of this as we study organic reactions. So this is a concept that's really important to keep in mind because it'll explain a lot of the observations that we make in the future. Now, what if we were to have a two-step mechanism rather than a single-step mechanism? How might that look when we look at our energy diagram, for example? Okay, a two-step mechanism means that instead of going from a starting material directly to a product, we're going to first go to some kind of intermediate structure, and then that intermediate structure is going to continue on to product. Okay, so if we had a two-step mechanism, then we have two transition states, one for each step. So let's say that we have our starting material energy somewhere here, and at the very end we have our products. Let's assume that we have an exothermic reaction. And because that's going to be true, most of the reactions we're going to be studying that are of interest to us are interesting because they're spontaneous, because they're favorable and exothermic. Okay, and if it was a two-step reaction, then instead of going straight from starting material to product, we're going to stop somewhere in between at an intermediate. And so the step one is to go from your starting material to the intermediate. Okay, and that's going to require going through some kind of transition state. We'll call that transition state 1. And then after at the intermediate, it's going to have to go up again to some other transition state before it can get to product. Okay, and it doesn't matter too much who's higher in energy. Of course, that's going to depend on the exact reaction we're looking at. This is just the overall picture that we're going to have. Okay, now when we have a two-step reaction, we can describe one of those steps as the rate determining step. And the rate determining step is going to be the step with the highest energy of activation. The step with the highest energy of activation is going to be our slowest step. So the rate at which that step occurs is going to define the rate of the overall reaction. Okay, so let's take a look at this example, this diagram, to see where we have our rate determining step. The energy of activation for our first step is here. We go from our starting material up to this transition state, energy of activation 1. And the energy of activation for the second step is going from this intermediate up to the second transition state. This is energy of activation 2. So in this example, where would our rate determining step be? Well, this is a much higher hill to climb. This is going to be a much slower reaction. This will be our rate determining step. So it's whichever step is the slowest step and the step with the highest energy of activation we call our rate determining step. Another thing to consider if we have a two-step reaction or a multi-step reaction is taking a closer look at these reactive intermediates. These are the species that are involved in the reaction. They are going to be high energy species, meaning they're unstable. So the relationship between stability and energy is another understanding that we have to have in order to fully understand organic reactions, or any chemical reactions really. Okay, and the good news is that chemicals and chemical species are a lot like humans in this respect. If you are a very low energy, stable person, right? You're calm, you're cool, you're relaxed. You could be described as stable, and you can be described as having very low energy. And molecules would be the same. A very stable molecule would have a very low energy. Okay, however, if you are a very high energy person, you are very unstable, you're always on the verge of exploding or getting into a fight or something like that, again, molecules would be the same. If a molecule is very unstable, we would describe it as being a high energy species. Okay, so when we say that a reactive intermediate is something that's high energy, that's the same thing as saying it's an unstable species. And it's defined as an intermediate because it's produced in the reaction and then it's consumed. It does not appear in the net reaction. Remember, our net reaction is simply the starting materials that we add in at the beginning and the products that we recover at the end. So an intermediate is a fleeting species that is created and then continues reacting. It's not stable enough to stay on its own as either a starting material or a product. And it's different from our transition state. Now again, this will be more apparent when we actually look at some specific reactions and see the intermediates in the transition states. But the transition state is something that will have partial bonds, partial charges. Remember, the transition state is a very high energy maximum. A reactive intermediate has full bonds, full charges, so it's going to look better than a transition state, but it's still clearly going to be an unstable species. So for example, one reactive intermediate we're going to be encountering in organic chemistry is called a carbocation. A carbocation is a carbon with 3 bonds, and therefore it has a plus charge. Okay, if we look at this species a little more closely, how would you describe its hybridization? What is the hybridization of the carbon of a carbocation? Well, it has 1, 2, 3 groups around it. Any carbon with 3 groups around it will be an sp2 hybridized carbon. And what kind of geometry do you expect for sp2? We expect trigonal planar. So if we were to draw a sketch of a carbocation, we could draw those 3 R groups as defining a plane. And then what else does an sp2 hybridized atom have besides these 3 sp2 hybrid orbitals? It also has an unhybridized p orbital that's perpendicular to that plane. So here's a question. What if we ask what is in the p orbital of a carbocation? Are there any electrons in it? Well, there can't be. This is a positively charged carbon, so it has just 1, 2, 3 electrons around it for its formal charge count, which means that is going to be an empty p orbital. There are the 2 lobes of the p orbital. So what's in the p orbital? Nothing. A carbocation has 3 bonds. It is a trigonal planar species, and it contains an empty p orbital. And this is going to be a very important species you're going to be seeing involved in a number of mechanisms. So let's look a little more closely at the carbocation and what are some things that we should know about it moving forward. One thing that we should have an understanding of is the relative stability of different carbocations. Okay, clearly no carbocation is stable because it's missing an octet. It's got a positive charge and only 3 bonds. We know that carbon wants to have 4 bonds to be stable. Okay, but not all carbocations are created equal. We could describe a carbocation by saying how many carbon groups are attached to the carbocation carbon. So here we have a CH3. So this is just described as a methyl carbocation. This carbocation is described as a primary carbocation because it has just 1 carbon group attached. This carbon has 2 carbon groups attached, so we call it a secondary carbocation. And finally, we have a carbocation with 3 carbon groups attached. We call it a tertiary carbocation. And it turns out that the tertiary is the most stable of the carbocations shown. So that's more stable than a secondary, which is more stable than a primary, which is more stable than a methyl, and methyl is the least stable carbocation. We really don't ever want to draw a methyl carbocation if we can help it. Okay, well, why is that? What is there that changes this stability? Okay, well, the alkyl groups that are attached are described as being polarizable. Okay, that means that we can look at the cloud of electrons in that alkyl group, and those electrons can be drawn toward the electron-deficient carbocation. To be polarizable means that you can kind of stretch out your electron density. Okay, so we can draw that as, now of course a methyl has no alkyl groups, but a primary has this alkyl group, and it can share some of its electron density with the carbocation. So we could draw this arrow showing it's sharing its electron density. We would describe it then as being electron donating groups. Alkyl groups are electron donating groups inductively. So we're just talking about the effects of this sigma bond and sharing the electrons to the electron deficient carbon. A primary carbocation has one carbon group that can do that. A secondary has two carbon groups that can do that. And a tertiary has three carbon groups that can do that. Now, is that a good thing? Is that something that would be good for a carbocation? Yes. This is a stabilizing feature because a carbocation is electron deficient. So anything that can help add electron density to that center is going to help make it less electron deficient. So obviously tertiary has three groups that can do that. So this is going to be the best carbocation we can find. Our take-home message is that as you increase the number of alkyl groups on a carbocation, you increase the stability. What's the maximum number of carbon groups you can have on a carbocation? Just three, because a carbocation always has three groups attached, so a tertiary would be the best here. Now, this effect of donating electron density inductively is called hyperconjugation, and there's a way we can maybe draw a picture illustrating this electron donation and what's going on. And if we take a look at the orbital picture of this example of a tertiary carbocation, so here we have a carbocation. It's got an empty p orbital. It's got three methyl groups, and I've drawn out one of these methyl groups to show the CH bonds because there are electrons in those sigma bonds. It has the sp3 hybrid orbitals overlapping with the hydrogens. And what happens in this hyperconjugation is these alkyl groups can share the electrons in their sigma bonds and donate some of them to the empty p orbital. So this you get partial overlap between the empty p orbital and the sigma bond here, and what's going to happen is it's going to share its electrons. So this is a drawing that you can have and you can look at. Typically the way we just represent it though is with this arrow showing the inductive donation. That would be plenty. Now, one other way that we can stabilize a carbocation is by having resonance. So there's a few other carbocations that are exceptionally stable. One is described as an allylic carbocation. The word allylic means that it's next to a pi bond. So in other words, this carbocation is not on the carbon-carbon double bond. It's next to the carbon-carbon double bond. And every time you have this allylic relationship, there will be a resonance form we could draw for this, where this pi bond shifts over to fill that vacancy, and that moves the positive charge to the other side. Now, anytime you have resonance, that's going to be something that delocalizes the charge. And delocalization of a charge is always a good thing. It's always a stabilizing thing. So resonance is a great way to stabilize any molecule, but especially an unstable carbocation. Another example of a resonance stabilized carbocation is a benzylic one. The word benzylic means that it's next to a benzene ring. A benzene ring is a special group that has a six-membered ring with three pi bonds. That's called benzene. And so if you have it next to a benzene ring, you can have the same sort of resonance where this pi bond can move over. And that's going to move the positive charge onto one of the carbons within the ring. And because benzene has three pi bonds to delocalize, it can actually continue. This now is allylic to this pi bond, so we can have additional resonance. So actually a benzylic carbocation has multiple resonance forms, etc. You could continue moving this pi bond over. There are quite a few resonance forms you could draw for carbocations. So if you ever find an allylic or benzylic carbocation, those are exceptionally stable. So if we look at overall carbocation stability, the best possible ones we can have are those that are benzylic or allylic, meaning they have resonance stabilization, or maybe tertiary because it has three alkyl groups donating electron density. And those are going to be our great carbocations, the most stable carbocations, very easy to form. Those are all going to be secondary, and those are all going to be much, much better than either primary or methyl. Primary or methyl are going to be really awful carbocations. We're going to avoid making them We typically even go to the extreme of saying that these are not formed under normal circumstances. If we needed to invoke a mechanism that involved a primary or methyl carbocation, we would probably say that it's going to be so slow and so difficult to make that very, very high energy carbocation that the reaction would be described as no reaction. Now, another type of reactive intermediate that we're going to be encountering in organic chemistry is a free radical. And so here are some examples of free radicals. This would be described as a chlorine atom. And this is a carbon radical. And in general, we could just represent a radical as some R dot, because what defines a free radical is something that has an unpaired electron. So rather than having an electron as either a sigma bond or a pi bond or a lone pair of electrons, it's a single electron on its own that's not being shared or paired up. Now, what is the charge of these free radicals? These are kind of interesting species. If you go to calculate the formal charge of this chlorine atom, you would add up 1, 2, 3, 4, 5, 6, 7. And when you check with the periodic table, you'd see that chlorine requires 7 electrons. So this is actually a neutral species. There's no charge. Same thing with this carbon. We would count it as 1, 2, 3, 4 electrons, and carbon's valence has 4 electrons, so this is also neutral. So most radicals that we're going to be dealing with in our organic mechanisms are going to be neutral species. Still, they are reactive intermediates. They are high energy and unstable, even though they're neutral, and that's because they're missing an octet, right? None of these, we always know we want to have this magic number of 8 electrons, so if you have an odd electron anywhere, then you can't ever be at 8. Now, the geometry of a carbon radical is approximately planar. It's either sp2 hybridized, it could be described as sp2, or it's a rapidly inverting pyramidal. So you could either draw it kind of like we did the carbocation with a single electron in the p orbital that could be above or below the plane, or you could show it as an sp3 hybridized, which would make it a tetrahedral arrangement we describe as pyramidal because it has just 3 bonds. But if it is pyramidal, it's rapidly inverting, so you would have inversion of stereochemistry. It's not possible to have a chiral radical because it's essentially planar. So either one of these drawings is good. A lot of times you just draw it in the p orbital here. And if you take a look at a carbon radical, you might kind of wonder, is it electron rich? Is it electron deficient? Because you do see that it has the electrons here. But in fact, because it's missing an octet, it is an example of an electron deficient species. And so like carbocations are electron deficient, they have the same relative stabilities. So just like we saw for carbocations, the best radicals are going to be benzylic or allylic. Let's review what allylic means. Remember, allylic means that you are next to a pi bond. That would be an example of a allylic radical. A benzylic radical. What does a benzylic radical look like? It doesn't mean you have a benzene with a radical on it. That would not be a benzylic radical because benzylic means that it's next to a benzene ring. So you're not on the double bond, you are 1 carbon away. So you have an extra carbon. Now it's benzylic. Now you have that allylic relationship and you can have resonance. So remember, both of these are resonance stabilized. Tertiary is good because we have these 3 alkyl groups donating electron density. So just like a carbocation would like that electron donation, a radical would like that as well. And so these are all the most stable. Those are better than secondary. Those are better than primary. So here's an example of a primary radical. It has just 1 carbon group attached. Those are better than methyl. This is the least stable. Okay, but it's still possible to make a methyl radical. Remember, it's not so electron deficient like a carbocation. A carbocation is so electron deficient, it's positively charged. So this is a little less unstable, a little more stable. And so we will see methyl and primary, secondary radicals. These are all okay. But if given a choice, we're going to want to try and form a tertiary radical or maybe a resonance stabilized radical. Those would be our best. And Finally, if we were to, when we do encounter radical mechanisms, we need to think about how we would use curved arrows to show electrons moving. Okay, and let's think about this resonance of this allylic carbocation. This is actually called the allyl carbocation, this 3-carbon system. If we want to convert from one resonance form to the other, what we do is we pick up that pi bond and we shift it over to the other side. Okay, so that's what we've been using up to now. We could just describe as a regular arrow. Every time we use a regular arrow, it moves 2 electrons at a time. So how do we convert from this resonance form of the radical to this resonance form of the radical? How have these electrons been redistributed? Well, you can imagine breaking this pi bond and moving just 1 electron over to pair with the radical, and the other electron stayed behind, and that's the new radical. So what we're going to be using for our radical mechanisms is called a fishhook arrow. It's kind of got a barb on this one side, and that's what we use to move just a single electron. This will come in handy when it comes time to do either resonance for a radical or if we want to do any radical mechanisms. Thank you for